Pulse power enables us to do amazing research.
This is a really exciting field. There's lots of new physics to be learned.
All the fusion concepts are on the cutting edge of every bit of technology, and we need to make every part of the process as efficient as possible.
Pulse power is essentially getting as much energy into a small volume as possible, as quickly as possible. The Z machine is a quintessential example of that happening. To do that, though, you're entering regimes of physics where there are challenges that we can't study on Z properly. You can study physics that are relevant to Z on subscale facilities like Mykonos.
Mykonos has been in operation since 2010, based on a technology called the linear transformer driver. Mykonos was originally developed as a pulse power test stand to test the components that are needed for a linear transformer driver-based facility. We weren't doing any experiments with the facility. It was literally just firing the machine for the sake of firing it to test if things failed or not. And now we know all the components work, and so we want to actually use it to do something that is diagnosable. So experiments on Mykonos now are able to test subsystems of what we do on Z currently.
What Z does is take slow capacitor banks and then compress the pulses as the power converges radially towards the target. Mykonos is fundamentally doing the same thing, just 1/20th of the current.
80 kV, gate valve closed. There we go.
The facility itself is several square meters in size, and we deliver all that energy to loads that are on the scale of a centimeter.
We can study 5-10 shots a week versus 5-10 shots a year that you could get for similar experiments on Z. You can shoot a factor of 100 times more often in a given year at a factor of 100th of the cost, roughly.
An experimenter can get many shots on Mykonos, whereas they may try for years to get a single shot on Z.
We have staff members within Sandia that perform experiments. We also have a lot of university collaborators, graduate students that come here to run experiments, and our team supports them as well.
I use vacuum ultraviolet spectroscopy to look at neutral hydrogen that desorbs off the surface. We're trying to make Z more efficient by investigating contaminants coming off of heated electrode surfaces as the current pulse is applied. We're really taking these loads and heating them up really quickly, and that will thus kick off the contaminants that we really care about. It's a very, very quick process, and the light that we're capturing, we capture it in about 3 nanoseconds. It's definitely a huge challenge to do things on the order of, nanoseconds.
I'm studying the electrothermal instability. Understanding ETI, or the electrothermal instability, is understanding how current flows around impurities in metal. We're not getting uniform current flow because of these impurities. If we can come up with some sort of mitigation strategy for these smaller instabilities, we can hopefully avoid the bigger ones down the road. I'm a year-round graduate intern here at Sandia, and it's just a really inspiring place to be working. And I feel like I do valuable work here, even as an intern.
The research we're doing will dramatically impact how Z operates in the near future, and perhaps give us confidence in next generation pulse power facilities 20 years down the road.
This is just really challenging work. You're always learning. You're getting paid to learn something new every day, and that's really cool.
Everyone wins if we can get more current to the target. So whether it's through Z experiments or experiments on Mykonos that help us understand how a Z experiment will perform, it's all in service of that goal.